All right, this is the lesson video for AP Calculus BC, and in this video I'm going to go over sections 3.2, which is the section on the derivatives of log functions, and then also section 3.3, which is the derivatives of exponential and inverse trig functions. So there's a lot of derivative rules here. The main thing about this is that as we go through these rules, what you're going to see is the derivative rules that we talk about today are being built off of the rules that we've already discussed. So rather than deriving every rule with the definition of a derivative, once you get to a certain point that you know some of the basic derivative rules, you can start to create as many rules as you want. And so that's what you'll see as we go through both of these sections. So the first section here, the derivatives of log functions, this is just an example of creating a derivative rule from a known rule. And what you can see here is that we have y is equal to the log base a of x. And what we're trying to do is get the derivative of log base a of x. So just kind of a general log function, how do we take the derivative? Well, since we don't have a rule right now, what we start with is we're going to convert this equation, we're going to rewrite it in an exponential form. And so you can see here that I've rewritten as a to the y is equal to x. So converting that log equation into an exponential equation. Once we do that, now we know how to take the derivative of this equation implicitly because we have a derivative rule for a to the y and we have a derivative rule for x. So I take the derivative on both sides of the equation with respect to x and then just solve for dy dx. And now down here at the bottom, we have now created a new derivative rule for log base a of x. So we can keep deriving these rules over and over again, as many different rules as we want, as long as we're using rules that we already know to create the new rules. Okay, so here are just your log derivative rules. So there's 4 of them, but the reality is there's 2 of them here. This is the one that we just looked at, this first one. So it says log base a of x. When I take the derivative with respect to x, I get 1 over x natural log of a. Well, the better form of that would be what we call the general form. So rather than just assuming that the argument for the log is an x, we can have anything for the argument of the log, and we'll just say it's some expression u. And now if we just use our chain rule, now we've got a general derivative rule that we can use. So 1 over u natural log of a, and then this is where the chain rule comes into play, times du dx. So it's still kind of working from the outside in, just like we were doing before. And this is just a special case of log base a of x. If I have a base of e, so that's what a natural log is. It has a base e. Notice my derivative here would be 1 over x, and I don't have a natural log there. The reality is we have a natural log of e. It would be 1 over x natural log of e, but the natural log of e is 1. So we don't really need to write that. And then again, the general rule is really the one that would be the better one to know, which is 1 over u du dx. So here, instead of just having an x as an argument for the log, I've got a general expression u. Okay, so it shows this as 4 rules, but the reality is if you know these 2 general rules, those are really the 2 rules that you need to know because the other ones are just special cases of those 2 rules. Okay, so what I have down below here are some examples, and I just want to show you how easy one of these is, and then I'm going to have you work through some of these. So we've got y is equal to the natural log of x cubed plus 1. So the rule that we're going to use here is this rule. We've got natural log of u. When we take the derivative with respect to x, it's 1 over u du dx. So this is just one of those things where you have to practice with these rather than blindly memorizing them. If you practice with them, it'll be the best way to remember them. So here they asked us for y prime. Our u in this case is x cubed plus 1. So it'd be 1 over x cubed plus 1 times du dx. So times 3x squared. And really I could do this in one step, but just to make it really clear, this would be 3x squared over x cubed plus 1. Okay, so pretty easy to do. When you're taking these derivatives of log functions, there's not really a lot of complicated work to do, but there are some special things that start to come into play, and that's what you'll see on the last example here that I want you to try. So there's 4 more examples, and I want you to pause the video and try them. When you get to that last example, the one with the rational expression as your u, try to think about if there's an easier way to do this as opposed to doing the quotient rule that you would be required to do if you just take the derivative in the form that it's in. So pause the video, and when you come back, I'll show you the solutions. Okay, so here's what you should have gotten for the rest of these. You can see for this one, it's a log base 5. So the main thing is it's 1 over u, natural log of a. My a in this case is 5, and then times du dx, which gives me 15x squared minus 7. And then from there, I've got my simplified solution. If you're able to do this in one step, that's really my preference for you. Just get to the point where you can do this all in one step, because we really don't need the intermediate step there once you understand what the process is. Okay, for this one, we've got derivative with respect to x of x natural log of x minus x. Pretty straightforward. X natural log of x, we're going to have to do the product rule. And then again, just take the derivative. This one, you might need an intermediate step, but in the end, you can see that x times 1 over x minus 1 just simplifies those add up to make 0. And so we've got natural log of x as a simplified form. This next one, natural log of sine x. So 1 over u du dx. Just get cotangent x. Okay, so again, very, very simple. Now, the last one was the one that I wanted to show you, and this is the one that really you have to think about a little bit. If I just took the derivative in this original form that we were given, so in the original form, my u would have been that expression. And when I take the derivative of that using the quotient rule, it's kind of a mess. And I think I've mentioned this before. Whenever I possibly can, I try to avoid the quotient rule, because the quotient rule tends to involve a lot of just, irritating algebra that I have to deal with. And I would rather not have to do all of that if it's not necessary. So what I did here instead to simplify this problem is I used log properties. I know that if I have the log of a quotient, I can rewrite that as the difference of two logs. And so that's what my first step was. Rewrite this as the difference of two logs. In addition to that, I can continue to use log properties. I have natural log of square root of x minus 2. Well, that's x minus 2 to the 1/2 power. So I used more log properties and made that 1/2 natural log of x minus 2. Now that I've got this in this really simple form, taking the derivative is very easy now, because I'm not going to have a bunch of extra chain rule stuff I'm going to have to deal with. I got 1 over x plus 1 minus 1/2 times 1 over x minus 2. And you can see that's essentially what my final solution is. So when you're taking these derivatives with the log functions, just make sure you're really thinking through these before you just jump into it. Stop and look at the problem and make sure you're thinking about, what's the easiest way that I can approach this problem? Because a lot of times, if you just jump straight in and do the first thing you think of, you might be causing yourself a lot of extra work. All right, let's move on here. And the next thing that I wanted to show you was a special case that we look at when we're dealing with the natural log of an absolute value. So here we're just going to look at this general natural log of absolute value of x. And the derivative rule for the derivative of natural log of absolute value of x is actually just 1 over x. And notice that all reference to the absolute value just sort of goes away. And I want to show you why that is the case. And it really has to do with some of the stuff that we've been looking at recently with absolute value functions. So what I'm going to do here is I'm going to start by looking at the absolute value of, or the natural log of the absolute value of x. And I'm going to think about this as a piecewise function. I know that when I'm to the right of 0, natural log of x just looks like x. So that's for x greater than 0. I know when I'm to the left of 0, this looks like the natural log of negative x. Okay, and that's for x less than 0. At 0, we're undefined, obviously, so there's my piecewise function. Now, what I want to do here is I'm going to take a piecewise derivative. And to do that is pretty simple. So I'm going to take the derivative of natural log of absolute value of x. And for my two pieces of this, notice that when I do natural log of x, I'm just going to get 1 over x for the derivative. For the second piece, I'm going to get 1 over negative x. Now, when I do my chain rule, that's times negative 1. And this was the rule, the top rule was for the rule when x is greater than 0. And then this is for the situation when x is less than 0. Now, notice in the end, those are both equal to 1 over x. So it doesn't matter whether I'm to the right of 0 or to the left of 0, I get the same derivative because of that chain rule, changing the sign on the derivative there. So that's going to be the case anytime you're dealing with a natural log of an absolute value. You can just drop the absolute value because it's always going to be accounted for with that chain rule piece of it. That negative is going to end up canceling out. Okay, so here's a special thing that I want to show you that in a lot of cases it can save you a lot of work, but it's also a way that we can create really an infinite number of derivative rules if we choose to. So what we have here is we're looking at y is equal to 8 to the x. Okay, we already know how to take the derivative of that. We talked about that derivative rule back on the first day of derivative rules. So we know that the derivative would be 8 to the x natural log of 8. But I want to show you another way you could do this if you didn't know that derivative rule. So this is called the process of logarithmic differentiation. And what this involves is taking an equation that I'm trying to take the derivative of and rewriting it in a form so that if I don't know a rule, I can use rules that I already know. And like I said, this is going to allow us to create a lot of new derivative rules. So in this case, let's assume we didn't know the rule for a to the x. So the first step here is take the natural log on each side. And the reason we're doing that is we want to get rid of that exponent. So now we have natural log of y is 8, or x natural log of 8. Well, at this point, taking the derivative is really just a matter of, using implicit differentiation here. On the left side, 1 over y dy dx. On the right side, natural log of 8 is just a constant. So we have 1 times natural log of 8. And then from there, just solve for dy dx. And you can see that I have this y here as part of my derivative, but we know what y is equal to. We know y is 8 to the x. So we're just going to substitute that back in, and we got the same result we knew we were going to get, but we did it with a different process. So we used the process of logarithmic differentiation. Now, like I said, it wasn't necessary there, but I showed it to you that way so you can see the result is what you were expecting it to be. Now, let's go through and look at a problem where we can create a new derivative rule now. So let's say we had a function that was x to the x, and we want to take the derivative. Well, with x to the x, we can't use the power rule because the exponent is not a constant. We can't use an exponential derivative rule because the base is not a constant. So we don't have a derivative rule for this. So we're going to create one by using logarithmic differentiation. So same process here. You can see that the first thing we did was take the natural log on each side, which allowed me to get rid of the exponent. The exponent was the part of this that was not allowing me to take the derivative. So now that I have it in this form, take the derivative implicitly. On both sides, we take the derivative, and then just solve for dy dx. And it's the same process here. You would solve for, when you get to this step, you would solve for y prime or dy dx, and then your x to the x just came from this y right here. When you multiply it over to the other side, remember y was equal to x to the x. So now we've created a derivative rule for x to the x. Okay, so like I said, we can do that in a lot of cases to create new derivative rules. How we can also use it is in a situation like these. So we have two problems here that are dealing with situations where it makes more sense to use logarithmic differentiation than it does to actually use derivative rules that we know, at least for the second one. For the first one, we don't really have a choice. For the second one, logarithmic differentiation is going to simplify the process. So what I want you to do is pause the video and try both of these derivatives and see if you get solutions that make sense to you. Now remember, when you do this, the solutions are not necessarily going to be really nice, simple looking things, but it is going to be the derivative of the function. Okay, and then for the second one, the whole purpose is, yes, we could do it with the quotient rule, but if we did the quotient rule, it would be a gigantic mess. So we're going to try to do this derivative in a simpler way. Okay, so take a second, pause the video, and work through both of those, and I'll show you the solutions. Okay, so here's the first one. You can see that we didn't have a derivative rule because we have a base with an x and we have an exponent with a cosine x in it. So we have no derivative rule for that. So I took the log on both sides, and then from there just took the derivative of the equation that I have. So derivative implicitly, you can see we kind of have a mess on the right-hand side, but it is something you can take the derivative of. And now when we get to that step where we've got this 1 over y here, I multiplied the y over, And then the one thing I always want you to make sure that you do is when you take the derivative when you take the derivative with this logarithmic differentiation, you always want to make sure that you get your derivative in terms of a single variable when you can. So this step, that is the derivative. But that's not really a good form for me to work with, because if I need to work with this derivative, I need an x value and a y value. And if I need to take a second derivative, well, now I've got to deal with that whole mess with having a y in there. So I'd rather not do it that way. So all we do here is just substitute the y back in. And you can see we don't really have a nice looking derivative, but that is the derivative of the function. Okay, so not that difficult to do. You just got to be careful with the algebra on these. All right, let's take a look at the second one. So this is the one where you can really save yourself a lot of heartache by using logarithmic differentiation. We've got this 3x plus 7 to the fifth over cube root of x plus 2. So when I look at that, your first thought might be quotient rule, and that wouldn't be wrong. However, we always want to think about what's the easiest way to do it. Well, the easiest way to do it is to rewrite this in a form where I can get rid of all of that quotient rule stuff. So if you think back to that problem we had on the first page of this, there was a problem that had the log of a quotient. Well, if I take the log on each side, that's essentially what I end up with, is the log of a quotient. And now I can just use my log properties, and I can rewrite what was on the right-hand side into this, and now the derivative becomes very simple. So on the left side, you have to remember your chain rule, 1 over f of x times f prime. And then on the right side, just use your natural log derivative rule. And then the last part, don't forget to substitute back in for the f of x that you have after you multiply it over to the right-hand side. Okay, so pretty simple and something that can save you a lot of work. Like I said, we use the logarithmic differentiation method for two things: simplifying difficult problems into a form where the derivative will be much easier, and also just to create new derivative rules. Okay, so there's also some stuff in this section that I don't want to spend a lot of time on, but it's the whole idea that if we were to look at 1 plus 1 over x to the x power, we took the limit as x approaches infinity, we would get the natural base e. So the limit of that as x approaches infinity is actually equal to e. And that's something that you probably saw in pre-calc. Well, the idea here is that we can actually derive that natural base. We can figure out what it is by using the idea of derivatives that we know. And so that's what is being shown here, the derivation of the natural base. This is one way you can find it. All of the stuff that we do with natural logs and exponentials with a base e, these things are all intertwined, and there's a lot of different ways to show how they're related. And that's really what's going on here. We're using the definition of a derivative at a point, and then we're using that to show that e is actually equal to the limit that I showed over there, the limit as x approaches infinity let's see, what was it? The limit as x approaches infinity of 1 plus 1 over x to the x power. Or we can write it in the form of the limit as x approaches 0 of 1 plus x to the 1 over x power. Okay, so not something you necessarily have to know how to do. It's just something interesting that you can do now that we kind of know these methods and these derivative rules. All right, so let's move on. In section 3.3, we're going to talk about more derivative rules. And it's going to be a continuation of the same things we've been talking about. We already talked about the basic derivative rules for a to the x and for e to the x. Those can both be derived using the definition of derivative. All we're doing with these first two derivative rules is just writing them now in a general form. So rather than having an exponent of an x, we can have an exponent that's any expression on both of those. So if a base a or a base e. And remember, base e is just a special case of having a base a. So even though there's two derivative rules there, it's really the same rule written two different ways. For this rule, the second one, natural log of a becomes natural log of e, which is just 1. Okay, so it looks like two rules, but like I said, really just one rule. All right, so I've got a couple of examples that I want you to try here, and I just want you to take a couple of minutes and work through these. So there's two examples, not anything difficult about them, but pause the video, work through those two, and then I'll show you the solutions. All right, and here are the solutions that you should have ended up with. You can see the first one, e to the negative x squared plus 1. That's an e to the u. So my du dx was negative 2x. times e to the u. Okay, so second one, I've got an a to the u, so I'm going to do a to the u natural log of a times du dx. Again, really simple to do. Okay, so let's move on. The last thing I wanted to show you here are the derivatives of the inverse trig functions. So when we do derivatives of inverse trig functions, these are new derivative rules. However, to develop these rules, we're not going to use the definition of derivative. We're going to use the whole idea of rewriting our equations in a different form and using rules that we already know, along with implicit differentiation, to create new derivative rules. So I'm just showing you one of these so you can see how it works. We have y is inverse tangent of x, and we want to find the derivative of that. So we want to know what's the derivative of inverse tangent of x. Well, we don't have a rule for that. So you can see the first step here is to rewrite this in a form where we've got functions we do know how to take the derivative of. Take the tangent on each side, we get tangent y is equal to x. And now when I take the derivative on both sides, I get secant squared y, dy dx is equal to 1. And now I'm just solving for dy dx. Now you can see we end up with this. dy dx is cosine squared y. That's perfectly fine as the derivative. However, like I mentioned before, we really want to write the derivative in terms of x if we can. So what I'm going to do here is use this whole idea that we had up at this earlier step. So that step we said tangent of y is equal to x. Well, think about what that means in terms of a right triangle, and that's what diagram I have drawn over here. My angle would be y, and when I take the tangent of that, I would have to do opposite over adjacent. So my opposite over adjacent, you can see the opposite is x. The adjacent side would be 1. So now I can create that right triangle. The hypotenuse would be the square root of x squared plus 1. Well, now think about what's the cosine of y, because that's really what we were interested in, right? We were down here. Cosine of y is going to be the adjacent over the hypotenuse. So 1 over square root of x squared plus 1, and then we square that. And now we have a derivative rule of 1 over 1 plus x squared. Okay, so not really difficult to derive them, but there are 6 derivative rules for the inverse trig functions, and they can all be derived that way. You don't really want to derive them every time, so these are rules that you're probably better off memorizing. Here's the one for inverse tangent of x, and then the derivative just as the general inverse tangent of u. Okay, so just using the chain rule. All right, so there's a couple of examples here that I want you to just quickly try, taking the derivative of an inverse tangent and then writing the equation of a tangent to the graph using an inverse tangent. So take a minute, work through those, and then when you unpause the video, I'll have the solutions for you. Okay, and here's what you should have ended up with. For the first one, really simple, 1 over 1 plus u squared times du dx. I just did it all in one step. I didn't even simplify the denominator. You can if you want. Sometimes it's nicer to have it written out in this form where you've got the 3x plus 2 still squared, because if we're going to work with that further along, sometimes it's nice to have reference to that original expression. The second one, the main reason that I gave you this, I know it's a really simple question. The main reason I gave it to you is because I just wanted you to see that when I write the equation of the tangent line, I can write it in an exact form. And this is a little bit weird when you first see it, because you're not used to having something like an inverse tangent as the y-coordinate. But if I want the exact tangent line, you can see that what I've done here is, first of all, took the derivative and got 1/5. But for the actual point that my line has to go through, when x is 2, y is the inverse tangent of 2. So now it's just y minus y1, which is inverse tangent of 2, is equal to the slope times x minus 2. And this would actually be my answer, and that would be the way I would prefer that you write your answer. Try not to get in the habit of just plugging everything into the calculator, because typically we want exact solutions. All right, so last part of this, I just want to go through the rest of those derivative rules, and I've got a couple of examples for you to work out. So these are all the inverse trig derivative rules. And you've got 6 rules here, but really if you can remember 3 of them, then the other 3 just kind of match up. So what I mean by that is look at these 2 rules. So inverse sine and inverse cosine. They look almost identical except for there's a negative here. And you could derive that using the same method we used for inverse tangent, but you would see that you end up with a negative for the inverse cosine, you end up with a positive for the inverse sine. So 1 over square root of 1 minus x squared. And if it was in the general form, it'd be 1 over square root of 1 minus u squared times du dx. Okay, so same idea. For inverse tangent, that's the one we looked at. Again, notice these two. Almost identical, the only difference is the negative. So again, even though there's 6 rules, there's really 3 of them that you need to know. And then the last one for inverse secant, you can see these 2 rules, again, look almost the same except for the negative there. So if you want to derive those on your own, you can, but the main thing is you have to know all 6 of these rules. So really, if you can remember these 3 rules and then remember which ones they match up with, then it's pretty easy to actually go through and memorize the other 3. So what I usually do is just practice with them. Once you practice with them enough, you'll know them. If you try to just blindly memorize them, that's kind of difficult to do. But if you actually go through and work with them a few times, you'll find that you remember them pretty fast. Okay, and then the last part of this, I just want you to work through these 3 examples, not because they're difficult, just because I want to make sure we talk a little bit about the algebra that shows up when you solve these out. So pause the video, work through those 3, and then when you come back, I'll show you the solutions and just talk about some little things you need to be thinking about. Okay, so here are the solutions for those 3, and here's the first one, inverse sine of x over 2. So what we have is 1 over the square root of 1 minus x over 2 squared times 1/2. Now, this is not an incorrect solution when we get to this point right here. However, it's not simplified because we've got a complex fraction. So if you were to work this problem out and it were a multiple choice, or you're working a problem out of the book and you check the answer in the book, you might get to that point and then look at the answer and think, well, my answer is totally wrong. The reality is your answer is right. You just have to do a little bit of work to get to that simplified form. So what I did here was I got a common denominator within that square root, and then you can see that the 4 in the denominator can come out of the square root, and it'll cancel out with this 2 right here. And then from there, it'll get into the form of this 1 over the square root of 4 minus x squared. So that's a really common type of question you're going to see. So just get comfortable with that algebra there, that last algebraic step of dealing with that complex fraction. The one with inverse tangents are always the easiest ones when it comes to the inverse trig functions. There's not really anything special that tends to show up. But the last one here is the inverse secant of x squared. So you can see that the very first step, I really have my solution here. This is an okay solution. However, absolute value of x squared, I don't really need the absolute value. And so even though this is an okay answer, if you checked your answer, you're probably going to see your answer is in that form if you have like a multiple choice or you're checking answers in the back of the book. And the reason is because I don't need that absolute value for the x squared. I can drop it, like you can see here. And once that's dropped, now I can go through and I can cancel out an x here and I can cancel out the squared there, and I get a simplified form that is equivalent to the one we started with. So keep that in mind. Whenever you have an even power within your absolute value, you can take it out of the absolute value. So even if you had like an x to the 7th, you could rewrite that as x to the 6th times the absolute value of x, and now you've got that x to the 6th factored out of the absolute value. So just keep that in mind when you're simplifying those, that you can take any even exponent out of the absolute value because you know that's going to be positive anyway.